Hi everyone. So far we've learned how to solve systems of linear equations using Gauss-Jordan elimination. And that process uses matrices. But we really haven't learned what matrices are other than just being a convenient tool for doing the calculations. This is the part of the class where we're going to gain some kind of a deeper understanding of what matrices are. And so we're going to start by talking about vectors. A vector is just a one-column matrix. So here are a few examples of vectors. A couple of things to note is that vectors can come in different sizes. And also, even though it's convenient to just talk about integers, we are assuming that the numbers could possibly be real numbers. And so I gave you an example where the entries are square root of 2, e, pi. Those are all possible. And in fact, you could have complex numbers, but we're not going to worry about that right now. So just a little bit of terminology and notation. The number of entries in the vector is the dimension of the vector. So here we have some examples where there's a two-dimensional vector, a three-dimensional vector, and a four-dimensional vector. And then the set of all n-dimensional vectors is written as Rn. This R with an extra line in it denotes the real numbers. And then that n in the exponent means that it's an n-dimensional vector with real number entries. So for example, we could say that this vector 2, 3, that's a two-dimensional vector, and so it's an element of R2. So geometrically, you could represent a vector in R2 as being an arrow in the plane. And so you'd start the arrow at the origin and then go to the point that has the same coordinates as the coordinates of the vector. Alternatively, it's sometimes convenient to think of a vector as starting at some other point in the plane, but having the same direction and length as the vector that we drew before. This would come up, for example, in physics when you're trying to describe the velocity of an object. That object is located at a certain place, and then you want to think of that velocity vector as starting at that point where the object is located and being an arrow that goes off from that point. Okay, so you can do arithmetic with vectors. And in particular, there are the following two operations. So the first operation is scalar multiplication. Scalar is just a fancy term for a number. I guess the idea is that scalar is supposed to be in contrast to vector. So a scalar is just a number. And when you have scalar multiplication, you're multiplying a number times a vector. And this just happens entry by entry. So for example, if I want to multiply 6 times the vector 2, 3, I would multiply the 6 times 2, and I would multiply the 6 times 3 to get 12, 18. And this has a simple geometric meaning, which is that when you multiply by a scalar, you change the length of the vector, but you don't change the direction. For example, when you multiply by 6, you end up with a vector that's pointing in the same direction as before, but now it's 6 times as long as it was before. And just one little caveat here is when I say it doesn't change the direction, it can change the direction in exactly the opposite direction when the scalar is negative. And in particular, if you multiply by -1, then that has exactly the effect of flipping the arrow in the opposite direction. So the second operation is addition. This is where you can add two vectors that are the same dimension. And the rule for how this works is pretty straightforward. You just add the components in each entry separately. So, for example, I would add here 2 plus 4 to get 6, and then I would add 3 plus 1 to get 4. And addition has a really nice geometric interpretation that goes by the name parallelogram rule. And the idea is that if you draw both of the vectors originating from the origin, then you can think of those two vectors as being two sides of a parallelogram. And then that new vertex of the parallelogram is the endpoint of the sum of the two vectors. And keep in mind that these new edges of the parallelogram could also be thought as representing the same vectors that are on the parallel edges. And so from that, you see that another way to interpret addition is taking the two vectors and putting them head to tail, and then seeing where they end up. And then finally, even though we've been doing everything for two-dimensional vectors, everything works exactly the same for higher dimensional vectors. So for example, if you have a vector in R3, you could also represent it as an arrow, but now it would be an arrow in three-dimensional space. Scalar multiplication and addition works exactly the same way. The parallelogram rule works exactly the same way. And even though it's difficult to visualize, the same thing happens with higher dimensional vectors. So if you have a vector in R4, that can be thought of as an arrow in four-dimensional space. And even though it's difficult to visualize precisely, just thinking of it that way can give you some intuition for how things work. So there is actually one more operation on vectors that's relevant for us right now, and that's called the dot product. If you have two vectors that are the same dimension, then you can take their dot product, and the dot product is a scalar. And the way it works is that you multiply the respective entries in each matrix and then add the results together. So in this example, you would have 2 times 1 plus 3 times 4 plus 0 times minus 1. And when you do all that, you get 14. So the dot product also has a nice geometric interpretation, which is that if you draw the vectors, and I'm intentionally not drawing axes here because it could be two-dimensional vectors, it could be three-dimensional vectors, it could even be higher dimensional vectors. But whatever they are, there would be some plane that both of the vectors are inside of. And you could look at the angle between those two vectors. And then it turns out that the dot product of v and w is the length of v times the length of w times the cosine of that angle that's between them. At this point in the class, the geometric meaning of the dot product isn't really going to play a role for us, but it is something that we're going to come back to later. So now we're ready to talk about matrices again. Let's say that you have a matrix with n columns. Let's call this matrix A, and let's say that V is an n-dimensional vector. There's a rule for how to multiply the matrix times the vector. And actually, it's one of those things where there are different ways of understanding the same thing. So we're going to start by understanding it one way. And this is called the row picture. So the idea is that you imagine that each row of A is a vector. Just to be clear, like before I was telling you that you should think of a vector as being a column, but you can also think of a row as being a vector. And so that's what we'd be doing here, is that we're thinking of each row of A as being a vector, calling them W1 and so on to Wm. Note here that the m is different from n, possibly. We're assuming that A has n columns, but the number of rows might be different from the number of columns. And then the rule for how to multiply A times V is that you take the dot product of each row of A with V, and those make up the entries of the product of the new vector. So for example, here's a matrix with two columns, and we want to multiply it times a two-dimensional vector. The way we do it is we look at each row of the matrix, and we take the dot product with the vector. So in this case, the dot product would be minus 2 plus 6 is 4. And so that 4 is going to be the first entry of the product. And then you move to the next row, and the dot product there would be minus 3 times minus 2 is plus 6, and then plus 3 makes 9. And then you move to the next row, and you've got minus 2 plus 18 is 16. And so there you go. We've just multiplied a matrix times a vector. One thing to keep in mind is that the dimension of the new vector is different from the dimension of the old vector. That has to do with the dimensions of the matrix. The number of columns in the matrix tells you what kind of vectors you can multiply the matrix times. And then the number of rows in the matrix tells you what kind of vectors you get after you do the multiplication. So at this point, you might ask, why are we doing this? What's the point? We're just making up new ways of doing calculations just for fun? No! The reason for doing this is that it gives us a new way to think about linear systems. So let me give you an example. Let's suppose you have a matrix. Because this matrix has 3 columns, it's something that you can multiply times a three-dimensional vector. But let's just write that vector as an unknown. When you expand out this multiplication, you get, in the first entry, 2 times x1 plus 4 times x2 plus 1 times x3. And in the second row, you'll get 1 times x1 minus 2 times x2 plus 1 times x3. And now you can sort of see what's happening here. The entries of the matrix are the coefficients in the expressions on the right-hand side. And this is exactly the kind of expression that you would see in a linear system. So just to be a little more specific, let's suppose I had a linear system like this. Before this lecture, what you would have done is just turn this system into an augmented matrix. And then from there, you could do Gauss-Jordan elimination and actually obtain the solution to the system, but you don't really have a good feel for what's going on there at a conceptual level. But now, based on what we've just seen, we've learned that we can rewrite this linear system as a matrix equation. And the value here is that we can sort of package this in a really nice way. We can label this matrix, so we'll call it A, and we can label the vector on the right-hand side, and we get this really nice way of describing the linear system as an equation AX equals B. And what we just saw here works in full generality. Every linear system can be rewritten as a matrix equation. And that matrix equation is really made up out of the same pieces as the augmented matrix that would correspond to that linear system. So the matrix equation is AX equals B, and the A is what's on the left-hand side of the augmented matrix, and the B is what's on the right-hand side of the augmented matrix. So in other words, linear systems are the same thing as matrix equations. So again, you might still be asking, well, what's the point of all this? Now we're just rewriting one thing in a different way. Are we going around in circles? Where are we going with this? Well, I can give you a bit of foreshadowing on where we're going with this. The idea is that we're going to learn how to do algebra with matrices. When I look at an equation like AX equals B, and the question is, we want to solve for x. What is the x such that AX is equal to B? Well, how do you solve for x? Well, what we'd like to do is just divide by A, and that would get x by itself, right? It doesn't always work quite as nicely. You can't just divide by A, but actually sometimes it does. And we're going to learn about when it does work and when it doesn't. And when it doesn't, what can you do as the next best thing? And that's all going to be part of the study of matrix algebra.